imagine if someone throws the ball up in the air, it goes in a straight path, it reaches a particular height, and it comes down. So imagine it was thrown from point O, it goes till a particular height. Imagine the height is h, and it comes down. Another example, if you throw the particle in a curved path, it goes in a particular curved path or trajectory and it comes down again to the ground. So there are two things we are observing. First is how the particle is moving, which I described, how the particle moved. An answer to this is explained in kinematics, which is the branch of physics where we study how the particles are moving in straight line, in two-dimensional space, in three-dimensional space. Then another question that comes to the mind is why the particle is moving. An answer to this is given in another branch of physics known as dynamics, which we are not covering today. We would be focusing on kinematics and try to answer the how part. Yeah, so humans have been wondering or questioning these kind of things, why the particle moves in a way as we observe. And these questions were there in the mind of human since very long in history as well. The Greek philosophers like Aristotle talked about this, how the particles are moving. And those were driven by mainly by philosophy or the natural philosophy, right? And then we had Galileo talking about moving particles, then Kepler talking about uh, planetary motions, and then we had Newton talking about how and why both parts, explaining the things mathematically. So there have been a evolution of explaining the motion of particles in past. Now we understand in details everything. Right. So before we proceed further, let's understand a couple of fundamental things. First, the position of the particle. What is position? Position is where the particle, and the key thing is where the particle is located. Particle is located at point P. What does it mean? Without having any kind of reference, does this mean anything? The answer is no, right? For that, uh, we have frame of reference and we use coordinate system for that. So this is three-dimension coordinate system, and we call this as x-axis, this as y-axis, and this as z-axis. What does it mean? How many steps do I need to move in the horizontal direction to get the position of the particle in the horizontal direction? And we call it as, say, x position x or x1, we can call, okay? How many steps do I need to move in the vertical direction to reach to this particle? And imagine this is y1 steps. So y1 steps are required, hence I wrote y1. How many steps do I need to move in the z direction to reach the particle? Z1 steps, so we are calling it as Z1 steps. So hence the position of particle is called as x1, y1, z1. These are the coordinates of the particle. So now I can say the position of the particle is at point P, described as x1, y1, z1, and without having any frame of reference or any coordinate system, this makes no sense, right? So what we are saying, our origin is placed in space here, as compared to this, the position is this, right? Meaning the position of the particle is essentially given by the coordinate x1, y1, and z1. So, right, so we would move further. This is the initial position. Let's call it as, say, P1. The particle can move to P2. Let's call this as point P2. And we are calling the steps as now x2, y2, and z2 steps are required to reach the particle at position P2. So particle has moved from P1 to P2, right? It could be straight line, it could be curved line. Straight or curved. It can be anything, right? So we are generalizing it. We understood the first quantity defining the position of the particle. The next one is velocity or speed. Before we proceed further, let's understand more about. Okay, before we proceed into the velocity and speed, I think all right. The next important quantity is distance or displacement. What does it mean? So particle moved from P1 to P2. Particle moved from P1 to P2. So particle has moved from P1 to P2. Uh, so hence the distance is P1 to P2. This is the distance particle has traveled. It could be a straight line or it could be a curved line, right? Understand this. So the particle is at P1 and the final position is P2. Particle could move in a straight line like this, or it could move like this. Care about initial and final position. We use displacement. So displacement is the difference of position, difference in position of particle through a straight line, which gives us the minimum difference in position, right? The shortest path, or we can call it as shortest path. Distance, however, considers the precise trajectory trajectory of motion, right? So here, when we in this example, the P1, P2, the straight line is displacement, and the curve path is distance. Okay, so P1, P2, this is the displacement, and the whole P1, P2, the curve path is distance. Right. So consider an example. If the particle started from point O, it moves like this and reaches the point O again. So initial and final position are same. Hence, what would be displacement? Hence, displacement would be zero, zero. But the distance would be non-zero. Okay. So we understood the second quantity. So we talked about the position of the particle, and then we discussed about distance and displacement. Distance is essentially the whole path traced by the particle, and the displacement only takes care of or cares only about the initial and the final position. In a kind of a situation where the particle moves in a path and reaches the initial position, the distance is non-zero, but displacement is zero. Now, moving to the next quantity, which is speed of the particle or the velocity. Right. So, speed of the particle is essentially how fast the distance is getting traversed or traveled. So it answers how fast particle is moving, right? So, and when we consider the displacement, for determining how fast the particle is moving, means the change in initial and the final position, displacement by time becomes the velocity. And I will be talking about vector and scalar soon, but velocity is a vector quantity. In the same way, displacement is also vector. I'll be explaining this. So displacement divided by time taken to complete this displacement is velocity. However, the speed is distance covered by the particle in time t. So what is t? T is time taken by particle to reach from initial position to final position. Right. Right. So in this example, where the particle moved from initial state to final state, and the initial and final states are same, in this case, velocity would be zero, but the speed won't be zero. All right. Let's move further. The last important quantity in motion is acceleration, which talks about how fast the velocity itself is changing. Right. How fast the velocity is changing. So it's a change in velocity in time t. That is acceleration. So here the time t is time taken by particle to change the velocity. Hmm? So we can write it as the final velocity as v2 minus the initial velocity as v1 and the time taken as t. This is also the explanation of acceleration. All right, so we understood the four key quantities: position, distance, and first was position. Second is distance and displacement. Third is speed and velocity, and fourth is acceleration. All right, now we will get deep into it. So, in order to understand it more conceptually and become enabled to solve the complicated questions, this might not be enough, and we should understand this more. Before proceeding further, I would like to talk about vector and scalar. So quantities in physics are categorized either in vector and scalar. And the examples are, for example, how hot the body is, temperature, how fast the particle is moving, velocity or speed, where is particle located, position. Um, and then we have the change in the position. So these kind of things which we have talked about. So this is scalar. Why? Scalar are the quantities which are not dependent upon the direction. And hence temperature doesn't, since temperature doesn't have direction, it's a scalar quantity. However, velocity, we saw it has a direction. And speed is scalar, it doesn't care about the direction. Position, position is also vector. Where is particle located? Does it have a direction? Yes, it has. How? Because in the coordinate systems, we determine the position of the particle that these many steps needs to be traveled to reach to the particle. Change in the position, yes, it's a vector as well. So hence the displacement is vector, and distance is also change in position, but it doesn't care about the direction. So it's a scalar quantity. How do we write scalar or vector? Meaning, if the particle is at position P, coordinates are x1, y1, and z1, and we will draw the same coordinate system x, y, and z. So in okay, so we write the position of the particle P, and we can represent it as position vector as r. And you see a sign above it. The arrow represents that this quantity is vector. X1 is the scalar part, meaning the quantity direction is given by I hat. I hat represents the vector in direction x. And then we have y1. In the same way, we have j. And then we have z1. We have vector k in z direction. So this is the position vector of the particle. Right. If we have to write the temperature, you need not to care about all this because it is scalar. Then the particle moves from this position P1. Let me update this as P1 to P2, and again X2, Y2, and Z2. In this case, let me update this to R1. So the R2 becomes X2I, Y2J, and Z2K. So this is the final position. Particle is at P2. And let's determine the change in the position. We can write it as final position minus initial position. So the change in position is x1, y1, x2 minus x1, y2 minus y1, and z2 minus z1. Okay. So this is also vector because we have changed it. And this because we have calculated the final and the initial difference in the final and the initial position of the particle, and this is known as displacement. Right? So it only cares about the particle initial and final position. It doesn't have any information about how the particle moved. Whereas the whereas the distance has that information. Distance cares um, about the information about how the particle moved from initial to final position. So this is the difference. All right. Now, if we have to calculate the velocity now, which is a vector, so the change in the position of particle from P1 to P2, particle moved from P1 to P2. So let me write this. Particle moved from position P1 to P2 in time delta t seconds, for example. Okay. So this is the velocity, right? So this is the velocity. And since we saw that this is a vector and the time is scalar, right? So dividing it would be something like uh, x2 minus x1 divided by delta ti, y2 minus y1 divided by delta t j, and z2 minus z1 divided by delta t k. Okay, so don't worry about these kind of long expressions. So essentially, I wanted to explain this, but we need to only care about or only understand that the change in the position of the particle in time delta t, if we divide these two quantities, we get a vector and it is velocity. Then the particle has moved from P1 to P2. And imagine the particle's velocity itself is changing. How do we write that? We call it as acceleration. And that is delta v, and it took time, say delta t. We can write it as v2 minus v1 vector, meaning at position. So what is v2? Imagine at position p1, velocity of particle at position p1 or p2, sorry. And in the same way, we have at p1. So there is a change in velocity. Particle got a kind of an acceleration, and we would understand all this more in dynamics. So because of this acceleration, the particle velocity got changed. And the reason for acceleration is actually force, that we will get into the details of it when we would be studying the dynamics. But for now, understand this velocity got changed, and hence we have acceleration there. And how much is the acceleration that can be derived from this expression? Acceleration is also a vector. Okay, so we understood all this scalar vector, and how do we calculate the velocity vector or the displacement vector or the acceleration vector. All right, so let's move further to understand um, and see some of the problem solving, right? How do we solve the problems? But before that, let me get some basic equations derived. And for that, you need to understand basics of differentiation, and that I'll cover in some different chapter. But please have a look at the basics of differentiation, right? So Imagine the particle is at position P and it got moved to position P dash. Hmm? And P dash minus P, it's a very small change. So there is a position change and we are calling it as delta R. And imagine it took time delta T, time taken to reach from P to P dash. Okay. So delta R by delta T is what? Velocity at point P. At point P means for this distance or for this displacement, the velocity is this. Let's assume the P dash is very near to P and we would like to calculate the velocity at point P. Then this becomes a very small quantity and we call it as dr by dt. So this is the differential essentially. And the velocity at point P, this is very near, infinitesimally near, and the distance is very, very small. This delta is very small, tending to zero, right? So we call this as velocity. We had seen this. Now what we are seeing, the distance, sorry, the displacement is very, very small, right? So we will generalize it V as dr by dt. And if we integrate this, and both sides, what will we get? All right, now we are going to talk about for three key equations for particle in motion. Particle in motion. And these equations will help us to solve the numericals as well. Okay. So let's consider a situation where particle is at point P, moves to point P dash. So it moves from P to P dash. And the displacement vector is delta R and delta T is the time taken to have this displacement. So hence, a couple of key equations we can write. Delta R, sorry, delta R by delta T is equal to velocity vector. And when we apply the limit where delta R and delta T are tending to zero, means the points are very near to each other. In that case, the velocity becomes the velocity of particle at point P is dr by dt. In the same way, we can write acceleration as dv by dt. That is also true. And let's do the integration. So dv, let's assume the initial velocity as v and the final as small v. Small u is the initial velocity, the v is final velocity, and then a dt. So a is also a vector 0 to t. Here the acceleration we are assuming constant. So it becomes like this. These are vectors. And then the final velocity can be determined by initial velocity using this equation. This is the first equation. And now using other things, means other relationships, we can derive rest of the things as well. Let's move. further, v can be written as what? dr by dt from this equation, right? U is constant, A is constant, and then we are going to apply the differential 0 to position R U into dt plus AT into dt. So we are going to integrate this as well from 0 to t. This becomes R and this becomes ut plus half at square. So this is the second equation to describe the particle in motion. In 3D, A is vector, remember. Now we will utilize these two equations. So from equation 1, we got T is equal to V minus U by A. Right, so we'll place this over here. So R is equal to U V minus U by A plus half A B minus U square by A. Mhm. So this becomes so it becomes R dot A now it's UV minus U square and 2 2U square. It's V square plus U square minus 2 UV. So this got cut and this became V square minus U square is equals to 2A dot R. This is third equation. So we got all the three equations. First equation is relating the final velocity to the initial velocity with acceleration. Sorry, I should have put this. Okay, so it's vector, right? And second is the position vector related to the initial velocity and the acceleration. And the third is uh, final velocity minus initial velocity square is related to this A dot R. With this, we have finished talking about three equations describing the particle in motion. And further, we would be taking few numericals to understand these concepts much better and deepen our knowledge in this area. Thank you.